Today, the topic that we are going to teach on week 12, Thursday, is yield criteria for ductile materials. And we still have to apply, 3D mold circle. Okay, so 3D mold circle will not go away. We still have to apply 3D mold circle on this topic. Okay. Now, so in the yield criteria, there are two commonly used yield criteria. And the first one, right, is going to be the first one is going to be maximum shear stress criteria. Is what we're going to do today. And for the maximum shear stress criteria is also known as Tresca. Okay, Tresca, I like to use the word tau to remind you that it's based on shear. And the second one, is based on maximum distortion energy criteria. Okay. So another word for it is von Mises. And what do I mean by the thing that is interest or mind-boggling a bit is what do we mean by ductile material? Okay, so for ductile material, the stress yield is a lot smaller than stress ultimate strength. Okay, so that's how we call or we say a material is ductile. Okay, so for brittle material, okay, the stress yield is approximately equal to the stress ultimate strength. So if we were to sketch a stress strain curve, okay, so this is our strain line, and this is our stress line. For a ductile material, you tend to see this, right? Straight line, ultimate strength, right? So this is what we call our stress yield. And when it peaks off, this is what we call our stress ultimate. So this is generally for ductile material. For brittle material, what you tend to see is it has a much higher Young's modulus, and the yield and fracture are very close together. So this is our stress yield. And over here, this is our stress ultimate. Okay, and this is for brittle material. Okay, so today we're going to concentrate on ductile material. We're just going to do one. So we're going to focus on maximum shear stress, okay, maximum shear stress criteria for ductile material. Okay, so the maximum shear stress criteria assume, okay, it assume that the yield strength in tensile and compression are equal. Okay, so if you load the material up in tensile and compression, okay, they are equal. But in real life or reality, right, the yield in compression, okay, the absolute value is greater than the yield in tensile. Okay, this is real life. Okay, but on this criteria, we assume them to be the same. Okay, so a criteria takes in the form that the maximum stress, okay, is equal to stress yield divided by 2. Okay, so we know, right, there's the maximum shear stress, and I'll call this equation number 1. And this equation number 1, the stress yield, where stress yield is equal to the yield strength, or is the yield strength, is determined experimentally. Okay, it's not what we calculate, but we have to do experiment. So equation 1, so tau max in this context, right, is a material property. Okay, so we know that equation 1 is a material property. Okay, so if you were to look into a table, right, so this table of material behavior, you have seen it before, right, this table over here. Let me right. So what we see over here, right, it is if the stress yield, they are quoting all these values over here. Okay. So I know you can see that it's tensile. Okay. So if you were to use this criteria as at compression, the stresses are the same. Okay, the magnitude is the same. Okay, whether it is in tension or in compression, okay, they are the yield strength are equal. So with this, we know, as I mentioned before, all this is quoted as principal stress. Okay, they are quoted in principal stress. So if I were to now sketch in terms of, let's relate this to 3D Mohs circle. So what we have, if we have a sample over here, and then this is carried out in tension. Okay, P1 and P1, we pull them. And if we were to, so if this is just my transformation, this is my X direction, okay, and then this is my Y direction, and then I'll call this my Z direction. So if we have an element here, okay, if we have an element here, so now I'm going to draw the element based on that transformation over there, right? So we have the element looking like this. Yeah, I'm ignoring the curve for now. I'm just drawing it flat, right? So we know under this configuration, we only have stress X, right? And there's no shear, no nothing. So if over here, this is our stress, sorry, I should draw a straight line. So this over here is our stress Z, okay? And this over here is our stress Y. So from here, we know that stress Y and stress Z are equal to 0. So now if we were to construct 3D Mold circle, right? We were to construct 3D Mold circle. Let me get into a different mode. So this is our normal stress, and it's in tension, and this is our shearing stress. Okay. And this is our normal stress, shearing stress element rotate clockwise, anti-clockwise. And because the structure is under tension, right? I'm going to draw a line over here. And this line over here is our stress X line. Okay. And stress Y and stress Z are the vertical line where we have normal stress is equal to what? Equal to 0. So we are aware that over here, this is our point X, and over here, this is our point Y, and also our point Z, right? Because you have no shearing stress. So when I sketch 3D mold circle, this is already 3D mold circle, okay? Because point Y and point Z are one circle, right? So this is our 3D mold circle. So we know that over here, this is our stress A. Our stress A is equal to 0. Over here, this is our stress B. Our stress B is not equal to 0, right? In uniaxial tensile test. So over here, what is quoted is our principal stress, which I will call this value over here relative to our mold circle, 3D mold circle. This is our stress B value. Okay. So in Pascal criteria, okay, what we assume, or is what we assume, we know that stress B or tau max is equal to stress B over 2 or stress U divided by 2, right? Why is that? Because we from the diagram or from the mold circle, the 3D mold circle, we know that this is your what? This is your tau max. And this will be equal to stress B divided by 2, right? Because Y and Z are equal to 0, okay? Now, so now you can visualize this now, and that is why in Tresca criteria, which I mentioned before, right? If you look at this particular steel, in tension is 250, in shear is 145. If you did not measure the 145 when you use Tresca criteria, let's say you did not measure in shear, okay? you can take the tau max is equal to 250